Hi guys, we're going to talk about area of polygons, and I wanted to go through this illustration with you. If you've talked to anyone from Mr. Parrish's class, this is the diagram that they discussed yesterday, and it just goes through several of the formulas for different figures and just analyzes where they come from. We talked about a couple of these, and I just want to review over all of them. If you can understand how they originated and where they come from, then it'll help you to understand the formula rather than just memorize it, because you've got to know these when we take the test. You will not have a formula sheet for the test. So we're going to start off with the easiest one, and you are going to get to see my fantastic drawings here. We're going to talk about a square. Okay, obviously the easiest one. So, square. If I ask you what the area of a square is, a lot of you all would say length times width, which is correct. But when we want to talk specifically about a square, the square has four sides that are all exactly the same. So if I give you one side as S, then all four sides would be S. So the area of the square, instead of length times width, more specifically, because it is a square, will be side squared. So 4 times 4, or 4 squared, means the same thing, but just more specifically for a square, this is how you'll see that written. Now it is, like you said, length times width, which we're actually going to use because we're going to put this with some of the others that you're going to have. We're going to use base times height, which means exactly the same thing, length times width. But since we're going to correlate this with some of the other figures, we're going to use base times height. So that's a square, pretty simple. All right, when you square something, just thinking in terms of algebra, you can think in terms of just a square, okay? Side squared creates a square because you're squaring something. It all correlates. It helps a lot of people when they're factoring, when they think of things like that. All right, so moving from the square, we're going to talk about the next shape, which is a rectangle. You all know what the area of a rectangle is. You know what a rectangle looks like. Make sure you note that they do have 4 right angles when we talked about the definitions, things that you have to make notations of with your figures. And the area of a rectangle is length times width. That's what everyone knows. But like I said, we're going to correlate that with base times height. Okay, so just like the square, you can find the area of a rectangle using base times height. But you can't use side squared, obviously, because not all the sides are the same. So rectangle, very easy. You all know this one. So it originates from the square in a sense that it is length times width or base times height, but that one's pretty simple. Now we're going to get into some where we're going to actually look at what shapes it used to be and how to understand what the formulas mean. So from rectangle, let's discuss a parallelogram. All right, now you all know what a parallelogram looks like. If I ask you about the properties of parallelogram, hopefully you would tell me that opposite sides are parallel, opposite sides are congruent. That's not the best picture. So it's similar to a rectangle, but it is tilted. And parallelogram, we've talked about the area of this before, but let's think about where it comes from before we actually talk about the formula itself. Whenever you think about a parallelogram, we could actually chop the parallelogram off, say, right about there. Okay, we'll just cut this whole piece out right here. And what we're going to do is we're going to pick that piece up and we're going to slide it down here and attach it to the other end. Well, if I do that, if I attach this piece down here at this end, this is what I'm going to get. And so what I've actually created, some of you all may see this already, is a rectangle. So by taking off this end piece here, just picking it up, moving it down here, and placing it on the other end of the parallelogram, you have created a rectangle. Well, what's the area of a rectangle? It's base times height. So that's exactly what the area of a parallelogram is. Even though it doesn't look like a rectangle, you can manipulate it into one, and it gives you the exact same formula. Now, something to make note of with your parallelogram, which most people don't miss this, but just to make sure, the height has to be the altitude. So it has to be what is dropped from that vertice straight down. And then your base is obviously the base of the parallelogram itself. So always be very careful whenever you're finding the height there for a parallelogram. But it is just like the rectangle. Now, branching off from parallelogram, we're going to have two different ones. So I'm actually going to move one up here so we have plenty of room on this paper. And so for this first one, we're going to talk about a trapezoid. Now, we talked about trapezoid earlier, a couple days ago. We talked about how we can chop the top of a triangle off and make it look like a trapezoid. And so we can get the formula for a trapezoid there. But then also have another illustration to show you for a trapezoid. So a trapezoid traditionally looks like this. Sometimes it's isosceles, which means the legs of the trapezoid are exactly the same. Sometimes it's not. But let's think about what this looks like. Okay? Some of you all may have put puzzles together, or you may have done some translations, rotations, flipping things, reflections. So if I were to reflect this or flip this trapezoid upside down and then translate it up here. So basically what I'm saying is flip the trapezoid on top of its base and then attach it to the end. Some of you all may have created designs where you just keep adding the trapezoids onto the end, whether you realize you were using trapezoid or not, you were. And let's analyze what we have here. Okay? When we're dealing with trapezoids, just like we have with parallelograms, we have to have that height that's dropping from that vertex straight down. So here's our height dropping from the vertex straight down. So this is our H. And in a trapezoid, we actually have two bases. We have one here at the top and one here at the bottom. So it doesn't really matter which end it's sitting on. Well, if I were to flip it and move the trapezoid over here, base 2 becomes the top and base 1 becomes the bottom. But what type of figure do I have? I actually have a parallelogram. Okay, here's my opposite parallel sides. Here's my opposite parallel sides. You could just forget about this line here in the middle. So by flipping my trapezoid and moving it over to the end, I've created a parallelogram. Well, what's the area of a parallelogram? Well, the area of a parallelogram is base times height. Well, to get my entire base, I would have to add base 2 plus base 1, so I could get the entire base of this trapezoid. Okay, so base 1, I'm just going to put this in order, plus base 2 would give me the base of that parallelogram, and then the height. Well, we're not talking about the parallelogram, we're only talking about the trapezoid, and it is half of this parallelogram. So that's where the 1/2 comes into play for the area of a trapezoid. Half the height times base 1 plus base 2. Another way that you could think about this, another formula that you could use, is height times the average of the bases. And just think about what that means. When you find the average of something, basically what you're doing, what you are doing is you're adding the two together and dividing by how many are there. Okay, well, average of the bases, add the two bases and divide by 2. Well, that's what you're doing. Add the two bases and divide by 2. You're finding the average and then multiply by the height. So that's just another way you can think of trapezoid. All right, the other type of figure we're going to talk about that we can get from discussing a parallelogram, we talked about this one also, is a triangle. And you all usually remember what the area of a triangle is, so that's usually not a problem. But I'm going to show you 3 illustrations One I'm going to give you is the parallelogram, like we just discussed. One I'm going to look at is a rhombus, which I'm going to turn on end like this, which remember a rhombus, all four sides are the same. And then of course just traditionally the square. A rhombus looks like a square. It's more tilted, probably more so than what my picture is there. But on all of these, I can create triangles. Okay? I can create a triangle with this side, and the height of this triangle would be the height of the parallelogram itself. And of course, this is my base. So I still have base times height, but I only want half of it. Same thing with my square. This is a side, this is a side, and here's my third side. This is my height, and this is my base. Of course, that would be the base and the height of the square. And then the same thing with the rhombus, if you were to draw the rhombus. Now, because this one isn't tilted quite enough as it should be, whenever you draw your three sides, this would not actually be within the triangle. You would have to drop the height outside of this rhombus. That would be the height, and then you would have your base. And again, for all three of these, you only want half of it because you're only talking about half of the original figure. So that's where the area of a triangle comes from, half the base times the height. All right, I want you to make sure you know these, look at these, and memorize them or understand them so that you can solve these whenever you get to your test or your quizzes. Now the other two that I'm going to run through real quickly, a rhombus, which we just discussed within the triangle, and a kite. And both of these can be drawn from the triangle. Now, I have to move through these kind of quickly because of time, but with a rhombus, if you were to draw your rhombus, and you were to think about all the sides are the same, if I were to try to create a square that connects the vertices, this square I would use base times height to find the area of that square. Well, the base of this square runs along this diagonal of the rhombus, and the height of this square runs along this diagonal of a rhombus. And now with your diagonals, you have your two diagonals are bisected there. So you're not taking the area of this entire square. It's basically taking these four triangles here and flipping them over to create the rest of the square. So basically you only want half of this red square. So, and it's length times width, or base times height. Base times height, those are your diagonals. But in a rhombus, since those aren't base and height, we call those diagonal 1 and diagonal 2. So for a rhombus, the area is half, because we only want half of that red square, times diagonal 1, diagonal 2. The exact same thing, I'm going to just draw this real quick, the exact same thing applies to the kite. Okay? A kite has, it will have these two diagonals. These two sides are the same, these two sides are the same. When you draw your diagonals, the diagonals have been bisected, so I'm going to give that 3. This one's going to have 4 marks. This one has 4 marks. Of course, these meet at a right angle. These do too. And again, you have, this case, a rectangle, but here's your base and your height, which is your diagonal 1 and your diagonal 2. And again, if I were to take this triangle and flip it here, take this triangle, flip it here, I would have that entire rectangle, but I actually only want half of it. So that's why the area of a kite is also going to be half of diagonal 1 times diagonal 2. So make sure you know all of these formulas and apply them to the worksheet you're going to do, as well as the quiz, test, anything we have coming up for the rest of the year.